Short circuit level is the amount of current that flows on the system during a fault. These faults can be caused by a lightning strike, weather conditions, or equipment failure. During the fault, the system can see a direct connection to the earth and current flows from all sources into it. SCL is vital during such a fault as it helps us to maintain system voltage. If we get a disturbance, then a stronger system will dampen it out quickly. It's just the same as how a strong bridge with reinforced joints would wobble but settle quickly when placed under force. If we operate a system with low SCL, it may take longer to recover after a disturbance. The short circuit ratio SCR is a measure used in power systems to indicate the strength of the grid relative to the connected generation capacity. It is defined as the ratio of the short circuit current at a particular point in the system to the full load current of the connected generators. A higher SCR indicates a stronger grid, while a lower SCR suggests a weaker grid. Large coal and gas generation create 5 times more fault current compared to wind and solar. A 100 megawatts generation would provide in the region of 500 to 700 MVA of short circuit level. Wind farms are limited by the rating their electronic component, so the same level of generation may provide only around 100 MVA of SCL. A short circuit current can be very large. If unusually high currents exceed the capability of protective devices, fuses, circuit breakers, etc., it can result in large, rapid releases of energy in the form of heat, intense magnetic fields, and even potentially as explosions known as an arc blast. The heat can damage or destroy wiring, insulation, and electrical components. An arc blast produces a shock wave that may carry vaporized or molten metal, and can be fatal to unprotected people who are close by. Fault current calculations are necessary to properly select the type, interrupting rating, and tripping characteristics of power and lighting system circuit breakers and fuses. Results of the fault current calculations are also used to determine the required short circuit ratings of power distribution system components, including bus transfer switches, variable speed drives, switchboards, load centers, and panel boards. Use short circuit analysis to determine fault currents either through simulation software ETAP, PSSE, dig silent, or manual calculations based on system impedance. Values SCR greater than 3 typically indicates a strong grid, suitable for integrating renewable energy or large generators. SCR smaller than 3 indicates a weaker grid, which may require additional stability measures when connecting new generation sources. Regularly assess SCR, especially when integrating new generation sources or making significant changes to the grid. Utilize software tools for complex systems to account for dynamic changes in the network. This calculation is crucial for ensuring system stability and reliability, especially in the context of increasing renewable energy integration. The short circuit ratio SCR is a critical concept in power system analysis. It is used to assess the robustness and stability of a power system when exposed to faults. A fault in a power system refers to a condition where the normal operating parameters are disturbed, such as a short circuit, which can cause dangerous surges in current. SCR is calculated as the ratio of the system's short circuit power, the maximum power available during a fault, to the system's rated or nominal power. This is the power available when a fault occurs in the system. It represents the capacity of the network to supply power during short circuit conditions. This refers to the nominal power rating of the generator or the system's normal operational power. The short circuit power is typically measured under conditions where the system is delivering maximum current during a fault, usually assessed during a transient state following a fault. In contrast, the rated power represents the normal operational capacity of the system under load. The SCR plays a vital role in assessing the fault handling capacity of the power system and can influence key aspects of system design, protection, and operation. Below are several reasons why the SCR is crucial. A higher SCR indicates a more robust system that can withstand higher fault currents. This means that the system has a strong short circuit power capability, and fault conditions will not destabilize the system. On the other hand, a low SCR indicates that the system may be more prone to instability and could lead to cascading failures if the fault is not cleared quickly. SCR helps in understanding how the system reacts to faults. A system with a low SCR will likely experience large voltage dips during faults, which can lead to equipment malfunction or even shutdown. A higher SCR indicates better system stability and less voltage drop during faults, leading to a more resilient grid. Protection systems are essential for isolating faults and preventing damage to equipment. SCR is used to set the proper fault protection levels, ensuring that faults are detected and cleared quickly without causing equipment damage or system-wide disturbances. Protection schemes, including circuit breakers and relays, are designed based on SCR to ensure that the fault current can be handled without causing excessive wear on the system. The SCR helps assess the strength of the power system. A high SCR suggests that the system has strong interconnections, meaning that it can tolerate faults in one part of the network without major disruptions elsewhere. This is particularly important in systems where multiple generators or substations are connected and need to work in harmony to maintain stability. The SCR can also have economic implications. A higher SCR reduces the risk of power outages or system failures, leading to more reliable service. This reliability is a key factor in minimizing costs associated with downtime, repairs, and potential damage to infrastructure. In contrast, a low SCR might necessitate additional equipment, such as larger transformers or more protective relays, which increases the overall cost of the system. Factors affecting SCR. Several factors can influence the SCR of a power system. The size and capacity of generators in the system directly impact the SCR. Larger generators contribute more to the short-circuit power and thus increase the SCR. The arrangement of the system, including the number of interconnected generators, transformers, and substations, can affect the SCR. A system with more generators or a stronger network will generally have a higher SCR. The impedance of transmission lines between generators and load centers affects the fault current. A higher impedance leads to a lower fault current and thus a lower SCR. The nature of the loads connected to the system can also influence SCR. Large industrial loads may cause a greater voltage drop and affect the SCR calculation. The SCR may vary depending on the type of fault: single-phase, three-phase, or ground fault, because different faults lead to different fault currents, influencing the short-circuit power. Example of SCR in a power system. Let's take a practical example of a power system to illustrate SCR. Rated power 500 MVA. This is the nominal capacity of the generator or system. 1500 MVA, the maximum power that the system can supply during a fault condition. In this case, the SCR of the system is 3, meaning the system can withstand fault conditions that involve up to 3 times its nominal capacity. A SCR of 3 is generally considered a healthy ratio, implying that the system has a high fault tolerance and is likely to handle faults without significant disruption. SCR and system stability. A power system's stability is often related to its ability to recover from faults quickly. If a fault occurs and the SCR is high, the system can absorb the fault current and maintain its operation. However, if the SCR is low, the fault current may cause instability, such as voltage fluctuations, equipment failure, or system-wide cascading failures. For instance, during a short-circuit condition, the voltage might drop drastically, and a low SCR could cause voltage instability, leading to system blackouts. Protection schemes are designed to detect faults and isolate them as quickly as possible. The SCR is a key parameter in designing these protection systems because it determines the magnitude of fault currents that protection devices such as circuit breakers and relays must handle. With a high SCR, protection devices must be robust enough to handle large currents. If the SCR is too low, protection systems might be over-designed, leading to unnecessary costs, or they might not be capable of managing the fault currents, potentially damaging the system. As renewable energy sources like wind and solar power become more integrated into the grid, the SCR becomes an important factor to consider. Renewable energy sources are often distributed and can introduce variability and unpredictability into the power system. In such cases, the SCR must be carefully monitored and adjusted to ensure the system remains stable, especially during fault conditions. Wind power plants, for example, often contribute to a lower SCR due to their variable output and the connection of wind turbines to the grid via inverters. This creates a situation where traditional protection schemes may not be sufficient, and special considerations may be required for fault tolerance and protection. Conclusion: the short-circuit ratio SCR is a crucial parameter in the analysis and operation of power systems. It provides insight into the fault handling capacity, stability, and overall strength of the system. A high SCR indicates that the system can absorb large fault currents without suffering instability or damage, whereas a low SCR signifies vulnerability to faults, necessitating additional protection measures and careful system design. By understanding and calculating the SCR, engineers can design more resilient, cost-effective, and efficient power systems that can withstand fault conditions and ensure reliable electricity delivery. Furthermore, as renewable energy systems are integrated into the grid, the importance of SCR will continue to grow, requiring ongoing analysis and adjustment to ensure system stability.